Yep. Everybody was really upset because it was like on HBO. My family spent money to get it. And then it was not that good of a fight. Happened pretty quick. My family lost a lot of money. Oh, a lot, I don't know. They were gambling. I don't know if they're gambling amongst one another. What?
Gambling roots run deep.
Oh.
It's tomato, bacon, mac and cheese that her mom made, and a Danish muffin thing. And I sampled bottle that I gave her that had sauce in it.
Did you like it? Did they like it?
The sauce?
Yeah.
Oh yeah, that's a
Yep. We're gonna finish up DFT today. So if you remember, we were kind of exploring density functional theory because this is one of the main computational methods that's utilized in theory today. There are other ones that are also utilized, but this is the one that's sort of favored by physicists. It was actually developed by physicists. So, what was this? Nobel Prize winner for DFT. Kohn. Yeah. For some reason, I don't know if that's what I'm thinking. Holmberg. Let me see real quick. I know. Total millennial move. Walter Kohn. Yes, it is Walter Kohn. Okay. For some reason, I was getting John Popel and him mixed up in my head, what they look like. He was a physicist, actually, and he won the Nobel Prize in chemistry. And on the day he won the Nobel Prize in chemistry, 2 Gen Chem students walked up to him and said, "We saw that you won the Nobel Prize in chemistry. Can you help us with a problem?" And he couldn't help them with the problem. That was kind of interesting. We talked about how functionals and the energy. What was the energy a functional of?
It was the complex energy.
Yep. How do we get the energy? It's not a wave function. What's the D stand for? Density. So what's, yeah. And we showed that we could combine terms. We said we had a non-interacting gas, and if it had the same density as an interacting gas, then the densities are the same. It's kind of interesting. We led us to a point where we were calculating the energy. We pretended things were non-interacting, and we were kind of just ignoring different parts of this and conglomerating it into one thing. All the problem child spots of this that we were just going to lump into one term. Do you remember what this term was for? It guessed specifically what type of energy. Yep, kinetic energy of non-interacting electrons. Then we had this term. Yep, potential energy for what? Yep. And then we had this electron-electron term. It's the classical one that you deal with in physics 2, most likely. And then, yeah. Yep. And what else are we, not just the kinetic energy that we're lumping in here, what else are we putting in there? Yeah, it is called the exchange correlation energy, but we have the correction to the kinetic energy, and what else do we have in here? Yeah, it's the quantum electron-electron interactions that happen here. So we have this thing called the exchange correlation energy, but it really includes corrections to the kinetic energy. So now we have this thing, but how did that actually help us? So question, how does this help us?
energy?
Can you say that one more time?
So it's a correction to the kinetic energy and the class.
Yeah, the electron.
So that one and the T.
Yep. And now the two quantum effects, we have electronic exchange. You guys probably haven't talked about electronic exchange really. But when you can distinguish the electrons apart from one another, there's an energetic penalty in there. It just comes from quantum mechanics, basically. Then we've talked about correlation energy, where the electrons all impact one another and you run into a many-body problem. Some people say that there's another theory called Hartree-Fock theory that does not get correlation at all, but it does get exact exchange. What they deem as the correlation energy is the energy that Hartree-Fock doesn't get. Some people call it. Okay, so how does this thing help us? So all we did, we said, oh, we have a simple system and we'll lump all this crap in here. And now in practice, when we go to do this, we have to calculate this thing. So we still have to figure this out. So how does this help us? There's a mathematical proof out there. And what this proof does is it shows that there must exist an exchange correlation functional that gets the correct answer. It's a pretty interesting proof. I really don't want to spend time going over it. You can read it in any PChem book that you find, but what it shows is there must be this exchange correlation functional that solves this term exactly. And this functional is called the universal functional. It works in all systems. So I said that there's other theoretical methods out there right now. Why isn't everybody doing this then? Scales very quickly compared to the others. So shouldn't we be using this? In fact, why are you doing experiments at all if this universal functional exists? Yeah, we got to figure it out. The proof says nothing about how to figure it out. People are utilizing machine learning to try and find ways to think of things that we really, as humans, can't conceptualize, but maybe the computer can define that thing. There are people who make different approximations and assumptions. So there's a large number of different functionals that behave differently. So the big point here is however, we have no idea how to get it. It's unfortunate. So then we run into the problem, how do we actually calculate this energy? It's a question. How do we calculate? Oh, I guess I should add a question mark here. No, actually you can. It's just never right. You make different approximations and you create a density functional that determines this energy. And through different approximations, it might either do a really good job for some systems, but it might do really bad for other systems. So for like organic molecules, there's a lot of organic chemists that like to use a functional called B3-lip. You don't have to write this down. My favorite one in my work I like opt PBE VDW. Devin, what's your favorite functional?
PB 0.
Yeah, that was pretty good. I like PBE a lot too because that's more classic, well, more conventionally physics.
A
So
lot of things right for us simulators.
yeah, I like a lot of Becky's stuff too. Axel Becky. If you're at a conference ever and you get a chance to listen to him talk, he is awesome.
Where's he from?
Canada.
Right there.
Yeah. He comes down. Well, actually, he doesn't travel as much as he used to. Some of these other guys, I'm not going to say who in PBE, but I've met somebody in PBE, and he is a giant jerk. All the above. Full of himself, really didn't develop the functional very much, but likes to take a lot of credit for it. If you can tell in terms of the acronym where he lies. But they didn't say his name. Fun fact, I called out Neil deGrasse Tyson in one of the other videos, and all of a sudden my views shot up. The algorithm is pointing people who are all about him to my channel, which is really weird. So I'm going to get a bunch of hate mail soon. Oh, I'm ready to. So if you look, this isn't even an extensive list. There's many different types of ways to do it. There are many different ways, resulting in many different functionals. So then the next question becomes, how do we pick one? So let's say you want to model something. How do you pick the best one? Or the one that you want to go with? Yeah, you could modify the conditions of the experiment. A lot of times, though, these are dealing with just like electron densities and things that we can't really perturb. They're just sort of there. How are other ways you would know you're getting a good quality answer? Well, let's think of your strategies. What would you do?
Think about your system.
Compared to what? Yeah, compared to others. What would be a really good comparison to make? Let's say I wanted to compute the NMR spectrum for, I don't know, 1,3-butadiene. I wanted to compute that guy. What would you do? Or let's go even better.
Get a sample and throw it into.
Yeah, compare it to the experiment. So sometimes you'll compute something that you know the answer to, and you'll compare and see how it does. And then you might apply that same computational setup to something you don't know and hope it's right. Yeah, that's what I do. I don't take the experiments either. Yeah.
So with functions, are there just sets of assumptions that you make that lead to a value?
Yeah, and honestly, it's like the mathematical formula and what it depends on. So like, for example, there's one called LDA, local density approximation, where it looks at the first derivative of the electron density around points. Then you have GGAs that look at the second derivative. Then you have meta GGAs. Can you guess what they do? Yep, exactly. They include some other terms too, but that's kind of a simple way of explaining it. But there's different ways to evaluate it, so just different mathematical formulas.
So, and I'm assuming based on systems, you can kind of guess which one will work better.
Yep, sometimes they are empiricized, so they've been fit to a set known values. Sometimes it might be just thinking about the way you could think about the electrons interacting with one another. But there are many different ways to do that too. So it's really like a philosophical argument in some cases there. Yep. So you can compare to others. So others in literature, you can compare to experiment. The other thing you can do is what's known as benchmarking. Basically what you're doing there is you throw it all at the wall. You try as many of them as you're willing to stomach or you can afford, and you see, do the results differ? If I'm using one type of functional that is meant to be better for certain systems, like for example, B3LYP star has been parameterized for paramagnetic systems containing iron, it should maybe do that better. BP86, which is way simpler, actually does better. Don't tell these guys because they get mad at it. So there's the other aspect, a grand one which you guys do not have, experience. And intuition. That can lead you to a lot of different spots. So when you give up most of your adult life to studying these things, you kind of get good at it. Okay, that's all I really want to talk about with density functional theory. Do you guys have any questions there? You're going to apply it later on in this semester when I give you electron densities. So they've been calculated from density functional theory, and you're going to do like band structure calculations or other stuff related to the solids themselves. The other thing is in PChem 2, you do a lot of computations. Are you talking about like how is this applied in industry right now? In industry, people model molecules sticking to surfaces. So like for example, if you have carbon dioxide going in, they want to make that happen and trap the carbon. Or in the refinery business, for example, let's say if something like that come in, you might want to make this. You can do it less expensive, but you can charge a lot for that product. That's a possibility. People in pharmaceutical industries, they usually have a target. So like you guys have talked about the lock and key model for enzymes or whatever. Oh yeah, so you have an enzyme that's going to cause some sort of biological response. You want to throw in a molecule here. You know what this looks like. You could screen a bunch of different molecules to try and get through and figure out which one's going to be the best drug. So I have friends who do that. You could calculate different properties. So like we were talking about NMR, you don't have an NMR around, but somebody might later on. Or for example, if you make, this is a completely fictitious scenario where we have a chiral center here, and this enantiomer completely cures morning sickness and the other one kills babies. How are you going to be able to tell them apart? You could use computations to help you out and give you some suggestions on which one you think are not going to kill the babies. This is what companies do. And hope it's right. In some cases, you patent things. So you have an idea, you do some calculations, and it looks feasible. You do some preliminary experiments and show it's going to work, and then you patent it, and then you're rich. It depends. There was a drug company for that, the Thalamid, that did not. Actually, no, this was an AIDS drug. They patented the wrong enantiomer, and they lost a ton of money because of it. So, yep. So in terms of doing this, we're doing it to get an electronic structure. but it is utilized heavily and it's becoming way more common. You're going to do it in PChem too a lot. A lot of industries lag behind doing this, but if you look at all the major, like big industries, they hire computational people. Small mom and pop places, probably not. Like ARG, I doubt has anybody who models. Probably don't know the value of it. Let me tell you, Exxon has a lot of people modeling for them. Pharmaceutical companies have a lot of people modeling for them. It's way cheaper to run some numbers than to do experiments. And you can whittle down your target from maybe potentially hundreds of billions to thousands. It's way more manageable.